Traditional security models rely on the operating system to protect sensitive data, but this assumes the infrastructure running that operating system is benign. In a hostile memory environment, the foundation underneath them shatters. Antivirus and operating system level security fail when an advanced threat compromises ring -1. That is the hypervisor layer, the system that actively manages and controls the virtual machines. Operating from this privileged position, a compromised hypervisor acts as a silent observer. It seamlessly forges audit logs and spoofs IP geolocation metadata, making a server appear as though it resides in Virginia when it is actively processing data in Moscow. The hypervisor can even pause the virtual machine's clock entirely. During this microscopic freeze, it scrapes the guest's memory for cryptographic keys and then resumes execution. The guest operating system registers no interruption and triggers 0 alerts. Software-defined trust is obsolete when the underlying infrastructure can manipulate the perception of time and space. To secure data in a hostile memory environment, we must abandon mutable software abstractions. We anchor trust to parameters an attacker cannot manipulate, immutable physical laws. First, we use the speed of light traveling through fiber optic glass to establish an unforgeable, hard metric for a server's geographic location. Next, we use the laws of thermodynamics, specifically the energy consumed during computation, to mathematically prove execution integrity. This approach produces a special-purpose sovereign apparatus enforced by silicon and network physics. Grounding the evidence chain in physical constants creates an irrefutable chain of causality, making data sovereignty a verified physical state. The first mechanism in this physical defense establishes a hard boundary. We restrict code execution to specific cryptographically secure silicon. Infrastructure as code deployments are strictly bound to designated hardware capabilities, specifically AMD processors equipped with secure encrypted virtualization, secure nested paging, or SEV-SNP. Inside this silicon, an on-die platform security processor encrypts the guest memory. This creates an opaque cryptographic barrier against the hostile host machine. At runtime, a hardware handshake measures the bootloader against a golden standard. Any deviation immediately forces a secure halt state. This hardware pinning makes it mechanically impossible for a workload to migrate to unverified external silicon, preventing teleportation attacks. Hardware verification proves what silicon is running, but it does not prove where that hardware physically sits. Standard IP geolocation data is easily manipulated by an untrusted hypervisor. To solve this, the system uses latency triangulation. It bypasses the operating system's networking stack entirely, utilizing raw network sockets to communicate directly with the network interface card. It sends precise packet pulses to verified reference points, known as alibi nodes, measuring the exact round-trip time. Because light travels through fiber optics at a constant 200 kilometers per millisecond, we calculate the absolute maximum physical distance of the server. If that round-trip time exceeds a strict threshold, for example 15 milliseconds, the server must physically reside outside the authorized sovereign perimeter. State-level actors cannot spoof physical location without violating the speed of light, making geographic residency a mathematically proven state. Even with location verified, a hostile hypervisor might still attempt to run introspection attacks directly against the encrypted memory. These silent observer exploits, like Spectre or flush and reload side-channel attacks, work by manipulating shared physical resources within the processor itself. But observation requires an exchange of energy. When a hypervisor inspects a virtual machine, it inevitably causes friction within the processor's Level 3 cache. To detect this, a microcode Sentry runs a continuous, highly deterministic mathematical fold operation deep within the processor's primary Level 1 cache. Instead of relying on vulnerable operating system clocks, the Sentry directly pulls the hardware timestamp counter to measure the exact physical execution time of this workload. A hypervisor can pause a virtualized OS clock, but it cannot stop the physical quartz crystal oscillator ticking on the motherboard. This graph shows our baseline cycle mean. If the hypervisor interrupts execution to peek at memory, it unavoidably consumes cycles. This creates measurable time dilation. We set a strict thermodynamic trigger. Any cycle variance exceeding a 3 sigma threshold immediately registers as an unauthorized intrusion. Operating at the microarchitectural level, This detection capability registers threats in fractions of a millisecond, outpacing traditional software-based monitoring by orders of magnitude. An attacker cannot observe the system without casting an unavoidable energy shadow. Invisible interception becomes physically impossible. Once a violation is detected, the system executes a fail-dead mandate. It prioritizes absolute data confidentiality over system availability. The defense targets the adversary's inherent latency constraint, known as the snapshot gap. A hypervisor requires over 1,000 CPU cycles to pause a virtual machine and successfully copy its memory state. This creates a microarchitectural race condition. The system must destroy its own sensitive data faster than the hypervisor can capture it. The software hurdle that ruins most standard defenses is modern compiler optimization. Features like dead store elimination silently erase standard memory clearing commands if they are deemed inefficient for runtime execution. To bypass this, the system executes compiler-resistant volatile writes. This forces the memory controller to physically overwrite cryptographic keys with high entropy noise, guaranteeing the sanitization instruction is never optimized away. Following the volatile wipe, the system initiates a process abort. This kills the application immediately without unwinding the call stack, bypassing any cleanup hooks a hypervisor might try to exploit. This hermetic panic achieves cryptographic suicide in under 100 cycles. It mechanically obliterates the data long before the hypervisor can complete its context switch. For compliance officers, defense contractors, and legal teams managing eDiscovery mandates, these capabilities reset the standard for secure cloud computing. This portfolio generates a forensic proof of sanitization based on time series physical measurements rather than spoofable audit logs. These specific patents interlock to secure the entire data lifecycle through verified physical constants. Immutable physical laws now enforce Geofencing mechanically. Vapor Audit provides a hardware-rooted verification environment for sensitive workloads. The acquisition VDR is now open for review. A mutual NDA is required for access.